The first application of superposition of waves that we're going to talk about is standing waves. We're going to start first with what's called standing waves on a string. So as a reminder, I want to come back to our demo, wrong demo, sorry, this wave on a string simulation. So I'm going to create a pulse. That wave pulse, let me adjust here, get damping down. As the pulse is created, we know the speed at which the pulse travels depends upon the tension in this string and the linear mass density. Now, something to notice is both of these two ends are fixed, meaning something is holding on to the ends of this string. When the wave reflects, it is inverted, meaning here we see it going up, and after the inversion, it's oriented downwards. A standing wave is created when a wave and its own reflection when they are interfering with each other. And so we're getting a wave pulse traveling in one direction, and actually not just the pulse, a continuous wave like this traveling in one direction, but then its own reflection traveling back. Let me add some damping since it goes a little crazy without damping. And so we get this string, as far as we can see it, just oscillating up and down in loops. It appears to us that this wave is just traveling very slowly to the right in this case, but that is just how we're seeing the interference. A standing wave is when the loops that we're seeing appear to be in the same place the whole time. So I have a different simulation to show you. Here we have two waves. So the blue one, this blue one right here, is one of the waves. This red one is another wave. And the function is set up that one of them travels to the right and the other travels to the left. Now, for example, if we look at this point right here, if we add the displacement of the blue and the displacement of the red, that's what this looks like. It might be purplish in color. The purple wave represents the addition, the superposition of these two waves. So at that point, they add to give us a really big amplitude. Right here, the positive displacement of the blue wave and the negative displacement of the red wave are canceling each other out at that specific location. So when I play this, we're going to see one of the waves traveling to the right, one of the waves traveling to the left, but then watch the purple wave. So again, the purple wave is this guy right here. Watch what happens. Right now I have it to play at really, really slow speeds just to picture that and see it. Oh, I gotta exit drawing, sorry. So this is at a very, very slow speed. We have the red wave traveling to the left, the blue wave traveling to the right, and this purple wave is essentially not moving right or left, but the amplitude is changing. And it's changing because of how the red and blue waves are meeting up at any one location. So when the red and blue waves overlap in phase perfectly, is when we're seeing twice the amplitude with the purple one right there. As it continues to move, that purple wave's amplitude goes down, it crosses 0, and then goes to an amplitude, maximum amplitude again, just oriented in the opposite direction. So these can represent a wave and its own reflection. That's what the red and blue waves would represent. And the purple is the overall, what we would see as an observer. Let me go ahead and speed this up. I think even 1 might be a little high, but let's see. Let's try it. So at close to normal speed, that purple wave, those amplitudes are changing back and forth really quickly. And this is what we would see as a standing wave. All right, I accidentally paused the recording instead of the simulation. So moving forward, here I wanted to show you one other demonstration. I found this video from our friends at Utah State. They are creating a wave on a string. It's actually a spring, kind of a slinky of sorts, but very tightly wound. It behaves like a string. And he's going to start shaking this string up and down to create a wave. And he's going to show us the simplest pattern. So it's called the standing wave pattern. And talk about the next pattern as well.
Holding it firmly, what was a peak heading toward him converts itself into a valley as it bounces off of his hands. So then a standing wave is where you pick a frequency that matches the length of the string in such a way that the waves created from my side of the string and bouncing off of Parker's coincide with each other and reinforce each other to create a standing wave pattern. The lowest frequency standing wave pattern is this one. It's called mode, M-O-D-E 1, or the first harmonic, or in other words, also called the fundamental mode.
So I'll go through those words when we get back to the whiteboard. But that simplest pattern is when we just see that one big loop in the middle.
Lowest frequency mode that you can get in a transverse standing wave. If I double the frequency of that mode, I get the second harmonic, second mode, and sometimes called the first overtone. And this one, if you'll notice, is going twice as fast as the fundamental mode. It has a node that's exactly halfway between Parker and me. And that's a node where there's approximately no motion going on.
Okay, so I wanted you to have a visual of what these standing waves look like. So let's come back to the whiteboard. The lowest frequency standing wave pattern. I guess since I have standing wave at the top of the page, I will just say this lowest frequency pattern on the string for a standing wave. So the string is anchored or held at both ends as the wave and its own reflection interfere with each other. We end up seeing this oscillate up and down with that one big loop in the middle. And as he mentioned in the video, this is mode 1. We're going to use an M. to represent this. It is also called the first harmonic or the fundamental frequency, or fundamental mode, I suppose I should say first. The frequency that creates this pattern is called the fundamental frequency. So depending upon the string, depending upon how long this string is, so how long between the two anchors, and depending upon how fast the wave is traveling, that determines the fundamental frequency. So if anyone's ever played jump rope, there was a certain frequency you had to continually twist that rope at to get the one nice big loop. You're creating a standing wave this way. So the fundamental frequency is the frequency that creates this specific basic pattern. We use an F1 from the mode 1 to represent this frequency. Now, a couple of things to make note of. The big loop portion is called an antinode. That's the constructive interference section that we're seeing. The ends are considered nodes. That's where we have essentially destructive interference. We have very little motion outside of the little shaking up and down we have to do to create the standing wave. Now, the wavelength of this wave is always directly related to the pattern. So if we think about a wave, if we were to graph a wave, we know a wavelength, let me draw that out a little further. A wavelength is always from one point to the next identical point. That is a whole wavelength. Oops. Well, if I come back to this pattern and I start at the left side and I follow my string, I go up and then back to the middle. So I go up and back to the middle. I am actually tracing out here 1/2 of a wavelength. So just following the pattern, going from middle up back to middle is 1/2 of a wavelength. And that's what I see on the length of this string. So from one node to the next is 1/2 a wavelength, which means the wavelength of this particular wave is twice the length of the string. That's kind of cool to be able to see that. The wavelength is always directly related to the string itself and its length. Now, coming back to frequency, we know the frequency of a wave is the speed of the wave over the wavelength. So speed of the wave over this wavelength, that's 2L. We can say F1 is the speed of the wave on the string over 2L. And L specifically means this length of the string that is actually vibrating, that's oscillating. The speed of a wave on a string, remember, depends upon the force of tension and the linear mass density. And so we can write this fundamental frequency as 1/2L, where L is specifically the vibrating length of the string, times the square root of the tension over linear mass density. If we play a stringed instrument, say a guitar, okay, I'm going to make it very maybe sad attempt at drawing a guitar. So the guitar strings all pass over the head up here, and they attach to pegs. Those pegs are used to tighten or loosen the strings to tune them. And then they're all connected down here as well. And so they all, without putting our fingers down on the string, they all have the same length originally. They're all tuned to play the note that they're supposed to play, but they're all tuned in such a way that the force of tension in them is pretty much the same. Because if it was not the same, we would get a net torque or moment on the neck of the guitar, and it would bend the neck overall. So the neck is where the strings go down. So to tune an instrument, we change the force of tension until the string is playing the note we want it to. The note we hear, the note or pitch we hear, represents the frequency that string oscillates at. Because however fast the string is oscillating is how fast it's pushing and pulling on the air molecules around it. And thus, it's the frequency of the sound wave that is created as well. Each string has different thicknesses, which means they each have different linear mass densities. And so thicker strings have a larger linear mass density. So thicker strings have greater mu. So they play lower notes, lower frequency notes. And we can see that mu is in the denominator here, which if mu gets bigger in the denominator, that makes this whole term get smaller when we're not changing anything else. So that's what this means. Now, on a guitar, if you want to play a different note, you can put your finger down on the string. If I put my finger down on the string, what happens is it only allows this portion of the string to vibrate. And that's a terribly over-exaggerated loop. But if I was to pluck that string, the portion of the string that would vibrate is only from where my finger is to where the string connects down here. So by putting my finger down, I'm shortening the vibrating length of the string. In my equation, that's what this L is. If I shorten the string, the portion that's vibrating, then the frequency that it vibrates at is going to be higher. Any stringed instrument at all, any problem you see that refers to a guitar, a violin, some sort of stringed instrument playing a note, we assume the fundamental frequency because that is always the primary pattern that is oscillating on the string. Whether you pluck the string or draw a bow across it like a violin, it sets up this lowest frequency pattern, this fundamental mode. And so we can jump to our equations here for the fundamental frequency. Now, as we saw in the video, if we double the frequency, our pattern, so it's the same string, but if we've doubled the frequency, we end up seeing two antinodes, so two big loops. The ends are still nodes, but we also end up with a node in the middle. This is considered the second harmonic or second mode. Similarly to what we did in the first situation, there's a specific length between the two ends. The section of the string that's vibrating has a specific length. But now, if I follow my wave from one side to the other, start on the left side, I go up, back to middle, down, and back to middle. I'm seeing a whole wavelength on the length of this string. So the wavelength is now cut in half compared to this fundamental frequency or fundamental mode, whichever way we want to look at it. So this pattern, if we want to talk about the frequency, we would have the speed of the wave, which depends upon the tension and the linear mass density, divided by wavelength, which is L. So notice, if we compare that back to our fundamental, we had V over 2L there. We now have just V over L. This is twice that fundamental frequency. This is why we had to shake it they had to shake it back and forth or up and down twice as fast in order to get these two loops. And again, we call it the second harmonic or second mode. We're going to use this M value of 2. He does attempt in the video to get 3. It's challenging if you have some sort of chord to try it with. If you shake it fast, oh, that's a terrible picture. Let's try that again. If you shake it 3 times as fast as the original. So the string, if you're able to shake it up 3 times as fast, you end up seeing a pattern with 3. I'm going to do just AN for antinodes. 3 antinodes, and now we end up with still the nodes at the ends, and then additional nodes in the middle. We call this the third harmonic, or the third mode. If we follow and trace the wave starting at the left side, we go up, down, back. That's a whole wave right there, but I have to finish tracing along the whole length of the string. So I'm seeing 1.5 wavelengths as I trace my pattern from left to right. I'm going to write that as 3/2 wavelengths on the length of our string. So what that means is the wavelength here is 2L over 3. When I put that into my frequency as V over wavelength, I end up with 3V over 2L, which happens to be 3 times that fundamental frequency. That's why we call this the third harmonic, this 3 times the frequency. We could keep going if we were to shake this string up and down 4 times faster, 4 times the fundamental frequency. We'd get 4 loops, 4 antinodes, and so forth. So we end up with a couple generic equations. So generic equations for these standing waves. And this is specifically the standing waves for the string or for any situation where you have a node at both ends. We find that the wavelength of whichever mode number, which we also call, so M is called the mode number or a harmonic number. It's still a multiplier, saying there's multiple modes in which we can get these standing waves. We use the term of mode or harmonic number specifically in this case of standing waves. So the wavelength of whichever mode is going to equal 2L over M. So the fundamental was M of 1. The second harmonic, or mode, was M of 2. Third harmonic, or mode, was M of 3. And we could keep going. A fourth harmonic would be M of 4. An eighth harmonic would be M of 8. M equals 8, rather. So this is one of our generic equations. Another is to say that since we know frequency is speed over wavelength, the frequency of the mth harmonic would be the speed of the wave over this wavelength, which ends up giving me mv over 2L. So the frequency of the mth harmonic, we just have to know which harmonic we're talking about, M. V is how fast the wave is traveling, and then L is how long the vibrating section of the string is. We can also say the frequency of the mth harmonic is that harmonic number or mode number times the fundamental. If we want the second harmonic, we have to shake the string twice as fast, up and down, in order to get the two antinodes. This equation, as I wrote above, if we're talking a string specifically, we could put in our equation for the force of tension over linear mass density and write it as m over 2L times the force of tension over mu. This equation works for our microwave ovens, for example, too. Our microwave ovens in our home that we cook our food with are standing waves. And they are standing waves such that there's nodes at the walls of the microwave. We can say that the frequency of the mth mode would be m times c, the speed of light, because microwaves are electromagnetic waves, light waves. So we could apply this in that situation as well. Now, for those of you that are musicians, that you do play an instrument, we can force out these harmonics. So on a violin or a guitar, if you put your finger down, so if this was my violin string, stringed instruments play the fundamental naturally. So you just pluck the string, you draw a bow across it, it will vibrate in this fundamental mode. If you put your finger very lightly on the string, you don't hold it down tight, then that allows both segments of the string to vibrate on both sides, and you start hearing the harmonics. And you can do that. If you put it here, for example, you could end up with the third harmonic. Now, for those that are not musical and you don't play an instrument, don't worry about that. Just use our equations we've been looking at. The thing to keep in mind is if a problem just says this violin is playing this note, then just run with the fundamental. Musical instruments play the fundamental naturally. And so unless you're told that you have a different harmonic, use the equation for the fundamental. So I'll go through a couple concept questions and problems, sample problems as well. And then we'll talk about the standing waves in pipes.